Now here's a trigonometric problem that was a bit tantalizing to me when I first saw it. It looks like something that should be readily solvable, but it it turned out to be a bit exasperating until I thought a little bit more about the problem. Now, here in this problem, you have three circles. You have a large circle and a smaller circle whose radius is half that of the larger circle. And the question is, what is the radius of the smallest circle that's inscribed between the tangent points and the tangent points of the circle and the tangent line that underlies all three circles. And so here I'm just drawing the triangle between the centers of the three circles. What you have to do here, now I initially tried to look at the triangle in the center, and it proved to be impossible. I used the law of sines, used the law of cosines, and nothing panned out. Not until I took a look at the triangles that were created by drawing the lines that you see here that I'm installing here down to the bottom tangent line, the base. And now I have a rectangle that is comprised of three triangles. And I know the sides of these particular triangles, and I use the Pythagorean theorem to find the hypotenuse of each of the triangles to find the base lengths, which I designate as M, L, and P. And M and P added together will give you L. And so once you use the Pythagorean theorem, you don't have any issue. So here I'm just drawing out the various parameters. I'm just showing here that the radius of the big circle is given as r, and the smaller circle I'm giving as a radius of r on 2. And so once we get going, it's just a matter of the application of the Pythagorean theorem 3 times. And it's interesting because everything falls out to a relatively simple answer. Now here you can see that I designated the base lengths M and P for the bottom 2 triangles. And I've written out the sides of the different triangles. Now the inner triangle is the hypotenuse of the triangles made with the dashed lines. And here I apply the Pythagorean theorem to the topmost triangle for L. I guess I was a little nitpicky, probably wasn't happy with the way sometimes I don't have the best penmanship. So here we have L squared, now we have M squared. And then once you obtain all 3, P squared, M squared, and L squared, you're all set. Because M plus P equals L. And that's it. You've got the problem solved. M plus P equals L. So we just throw in our representations for m, p, and l. We have to take square roots, of course, because what we have derived is the Pythagorean theorem, L squared, M squared, and P squared. So it's just a matter of taking the square roots of those quadratic equations or quadratic representations, and so I have M and P, and that equals to L. Just trying to make it neater, a little easier to read. On the right side of the equation is L. And that's the problem. It's simple. And I tried working only with the triangle in the middle when you really should be working with the triangles on the outside, circumscribing the center points of each of the circles. Now I used the second page to write out the equation because I didn't have enough room on the first sheet with the diagram on it, diagram of the circles. But this is that equation that we had, m plus p equals L. And all we have to do is just a little bit of algebra, and we'll boil it down to its simplest form. So all we do is a line by line simplification. First we expand each of the squared terms, and then we eliminate terms that cancel each other out. For example, in the first square root, x squared cancels out, as well does r squared over 4, that cancels out. But the rx is additive, so we have 2 rx there. So things will simplify once we expand these out. And that's what we're doing now. If you hear any crunching, I haven't had my breakfast yet, so that's what's happening here, having my breakfast. So what you can see here is that those big, nasty looking expressions simplified to these very, very small square roots. I do some factoring, and bring everything over to one side. So I isolate x on one side, on the left side of the equation. This is basically the equation here. I take care of r over r squared, and this is the answer. Now, by squaring it, I get the full answer. That is it. That's the entire answer. I box it in. Alrighty. That's all I'm trying to do is box it in. It's nothing that urgent. That's the answer. Now, in the case that was given on the website, I found this problem. I think it's Press Talk Walker or something like that. He gives the radius as being r, the radius r as being 4, And when you multiply this by 4, you have 8 divided by the square root of 2 plus 2 squared. And I think that's something like 0.68 for a radius, something like that. Now you can do this more generally and come up with a formula for all 3 radii and leave it at that. But this was a particular case where you were given R1 being 4, R2 being half that radius. And once you do all of the math, this is the end result. So it wasn't such a terribly hard problem at all once you look at the problem in the right perspective. So this is Mathman wishing you all the best.